Yes, hello and welcome to Magic 081 String Theory. My name is Thomas Mohaupt. I'm a theoretical physicist based in Liverpool. And well, my topic of research is string theory. Now, before we start with the contents of the first lecture, I would like to give you at first a few introductory remarks about the course. Okay. So let me start by saying a few words about what this course is about. It is meant to be a hands-on introduction to the foundations of string theory. From having taught this course for some time, I'm aware that the audience in this course might be quite diverse. So there will be people who want to do a PhD in string theory, but others who have taken this as part of their doctoral training and are interested in the topic, but it's not quite their main activity. I will try to provide something for everybody. And here's some advice for aspiring specialists. What this course can provide is help with getting started with the standard textbooks and reviews, which sometimes go relatively steep into the topic, so that you will appreciate a bit of help into getting into the subject. And for non-specialists, this will provide an introduction to a variety of concepts which are not only used in string theory itself, but in large parts of theoretical physics and applied mathematics, in particular modern particle theory, quantum field theory, gravity, but also in various branches of mathematics. Therefore, before continuing, I should also say something what this course is not about and what I cannot give. With 10 hours that we have together, this cannot be a comprehensive overview of string theory. If you really want to get deep into the subject, in addition, you will need to engage with the literature and receive guidance from your supervisor if this is your topic. On the other hand, it is meant to help you getting into an active learning experience. So it will not be a qualitative or entertaining approach, but I really will show you some basic work, how things are done, and you will get more out of this course the more you actively engage with the material. Given the small amount of time, only 10 hours, and that we will want to cover some material in this course, the way I have organized this is that since I can't give you much details of computations, these are usually left as exercises. So there are lots of small steps that you will need to fill in for yourself if you don't want to just take it on faith and believe me. And if you want to become an expert in the subject, this should be what you do. Try to fill out all the little gaps that I leave. Try to do all the little exercises that I suggest. Now, in addition, there will, of course, be also official example sheets. I plan that there will be 3 of them. And this is the absolute minimum of what you should do in order to make sure that you have learned the essential things that you should take home from this course. In particular, if you take the assessment, doing the example sheets will give you an idea of what will be expected in the final assessment. Now, this final assessment will take place in January. It will be a 2-week take-home exam. The amount of work that I will set is something that you will be able to do in 2 hours if you have followed the course actively. And it will provide you with feedback whether you have mastered the basic things of the course. So it will not be extremely demanding, but it will test whether you have gotten a selection of the key points of the lecture, key techniques that will be prepared by the example sheets. Traditionally, you sometimes also give a motivation for a topic, but given that we only have 10 hours together, I will assume that everybody knows why they have taken this course. I will not give you a lengthy introduction and motivation, and I will dive right into the subject. But before we do this, let me just check with you whether there are any questions at this point. I think you should be able to prompt me on the chat if there's any problem. And I suppose you could also unmute yourself and interject and ask a question if there's something unclear. Otherwise, I will now start with going through the material, sharing again my screen. And using my slides. And the first part of the course, will be about the relativistic particle. Now, I assume that many of you will already have some prior knowledge of the subject. And the idea here is, firstly, to fix notation and conventions. Secondly, it will be very helpful to compare what is different for a relativistic string compared to a relativistic particle. And finally, I would like to review certain key concepts of mechanics so that we are all on the same page and are prepared for the techniques that we will be using for the string. Good. So to set the arena for the relativistic particle, we start with setting up the kinematics. And the first thing is Minkowski spacetime, where, for reasons that will become clear when we talk about strings, I like to keep the number of spacetime dimensions arbitrary. Otherwise, the notation is quite standard. We use Greek indices running from 0 to d-1, and most of the time I will set the speed of light to unity. My convention for the metric is what you call the mostly plus metric. That means if you take the Minkowski scalar product between two vectors, it's negative for time-like and positive for space-like vectors. You might be used to a different convention. The mostly plus convention is the one used in string theory and also used by many people working in general relativity. In particle physics, people tend to prefer the opposite convention, and then there will be some unused or unusual minus signs for you. So for reference here, use letter eta for the Minkowski metric tensor, and the line element looks like given in formula 3 if you use our mostly plus convention. Now the kinematics, we want to talk about particles. So a particle in space-time will sweep out a line, so-called world line, like here. And to describe the world line, we will introduce a curve parameter, which tells us where we are on the curve. So here I've chosen a general curve parameter x of s, and this is then how such a world line is parameterized. Of course, these labels that we give to points on a curve are just labels, and we can change them. So I can always replace such a curve parameter by another curve parameter. I can replace s by s prime. And in order for this to be really a reparameterization, it needs to be an invertible map. Invertible map would mean that ds prime by ds is different from 0. Very often one also keeps the orientation, meaning the direction in which we are running through the curve, the same, and then ds prime by ds must be positive. Now in mechanics, we often use a distinguished curve parameter, and one of the distinguished curve parameters is t, where t is the time measured in some inertial frame. One quantity which is associated with this is the velocity, which is the derivative of position with respect to time. And according to special relativity, this velocity will be smaller than the speed of light for massive particles and exactly equal to the speed of light for massless particles. Now, this description is not Lorentz covariant, so one prefers to find a description of the particle where all the quantities are Lorentz scalars, Lorentz vectors, and so on. And therefore, instead of the time measured in some inertial frame, which is not a Lorentz scalar, one uses proper time, which we can do at least on time-like world lines. And this is a time moving in a co-moving frame, or loosely speaking, it's a time measured on a clock that I have attached to the particle. To see how this proper time relates to the time measured in an inertial frame, we can get an infinitesimal relation by taking the Minkowski line element and evaluating it on the curve, where the position x becomes a function of t, and then we can read off a differential relation between proper time and inertial time and integrate it up in formula 8 to get the relation for finite intervals of time. This then allows us to define the relativistic velocity, so the derivative of the point in Minkowski space with respect to proper time. And since we are differentiating a Lorentz vector by a Lorentz scalar, this is really a nice Lorentz vector which transforms covariantly. If you like to, we can then use our relations and express this relativistic velocity in terms of the non-relativistic velocity v. One point to be noted about the relativistic velocity is that it is normalized in the unit vector with a minus sign due to my convention that time-like quantities have negative square norm. Geometrically, of course, x dot is a normalized tangent vector of the world line. So if we draw our world line here, then x dot is a vector which is tangent to the world line and has a specific normalization that it is unit length. Now, one thing that we note already here is that proper time and hence relativistic velocity cannot be defined for light-like world lines and therefore not for massless particles, because I cannot attach a clock to a photon traveling at the speed of light to measure time there. So we will come back how we have to describe mass, or how we can describe massless particles a bit later. But for now, I'm carrying on and go to setting up the dynamics. Now, the most important dynamical quantity is the momentum. There's a relativistic momentum vector, which I get by multiplying the relativistic velocity with the mass of the particle. And again, I can express this in terms of non-relativistic quantities if I like. The mass is the total energy measured in the rest frame, whereas the total energy in a general frame is given by P0. And then there's this famous relation that called the mass shell relation. If I take the Lorentz square of the relativistic momentum, it gives me minus m squared. And by solving this for the energy, I get the famous formula that E equals mc squared if I'm in the rest frame. Otherwise, we have additional contributions from the kinetic energy. Good. Now, the most important relation for setting up dynamics is Newton's second axiom that tells us how particles behave under forces. So that relates the time derivative of the momentum to the vector of force. And if we are doing this in special relativity, then we have to use the proper relativistic momentum, which has its square root, which builds in the relativistic speed limit and is the correct relativistic version of Newton's second axiom. But of course, writing the formula in this form, it is not manifestly Lorentz covariant. There's a covariant form of this equation where we take the derivative of the relativistic momentum with respect to proper time and equate it to a Lorentz force, which is a relativistic vector. If you have done a course in special relativity, you have probably seen how this Lorentz force F mu is related to the non-relativistic force F. If not, I suggest to try this as an exercise and to work this relation out. Okay, now all fundamental forces in physics can be described in terms of a variational principle. So we need to talk about action principles. And first, I will show you an action principle for a free massive relativistic particle, which is not Lorentz covariant. So the basic object in this is the action. And the action is considered to be dependent, to be a function of the position and velocity of the particle. And it can be written as an integral over the world line, in our case here, maybe as an integral over time, if we parameterize the world line by time t. And the integrand is then called the Lagrangian. For free massive relativistic particle, the action is just given by mass multiplied by the proper time with a conventional minus sign. This should also say about my conventions that I've set the reduced Planck constant equal to unity. So this actions in these units are then dimensionless. And then the way the action principle works is the following. I consider the path of a particle between 2 points, which I keep fixed. And then I compare a path to a nearby path and ask whether the action then becomes larger or smaller. This is indicated here. I have a path, I make an infinitesimal variation, and this variation is infinitesimal, but otherwise arbitrary. However, I keep the endpoints of the variation fixed. So the initial point and the final point are made to stay the same. And then, by requiring that the action is stationary under this variation, I obtain the equation of motion, and I claim that for the action that I've given you here, it gives you Newton's second law, in this case without a force term, because we have not yet have added interactions to our action. Okay, maybe at this point I want to show you something additional, which I have prepared. Maybe this drawing here. Yeah, okay, this is the first slide where I just described to you how a world line of a massive particle is parameterized. So here we have a Lorentz coordinate system in blue, and in red is a world line, and one could either use an arbitrary curve parameter S along the curve, or for example, since this world line is time-like, you could take the inertial time t equals x0 of your chosen inertial system as the curve parameter. But actually I wanted now to show you probably this drawing here, which illustrates the variational principle. So again, here we can see in blue a trajectory for a particle x of t. We make an infinitesimal variation, keeping the ends fixed. And then the way we derive the equations of motion is we substitute the modified path into the action. Compare to the action evaluated on the original path. We Taylor expand the action evaluated on the deformed path and expand in a Taylor series in dx, since we take dx, delta x, the variation, to be infinitesimal. We only need to expand to linear order. And then we require that this is stationary, meaning that the so-called first variation here vanishes. So the action does not change under variation of the path to first order in the variation. And this gives you the equation of motion. And what I would also like to give you is some practical tips if you do this variation exercise. The first thing is the variation of the curve also determines the variation of the velocity. So you can pull time derivatives through the variation. Otherwise, the variation behaves like a first-order differential operator, in particular, if you make a variation of a function of x, this behaves according to the chain rule. And lastly, if you make a variation, you will have terms where you have a variation of the velocity, here delta of x dot. By the first rule, we can then pull the time derivatives through the variation. But in order to read off what the equations of motion are, we need to collect all terms proportional to delta x, and there should not be any derivative acting on dx. So if you have a variation of the velocity, then you have to do an integration by parts, and then from this so-called bulk term here, you can then read off what the equation of motion are by imposing that this variation of the action should be 0 for any variation delta x. But in general, this procedure produces a boundary term, which may or may not be relevant. For the point particle, this is of course not relevant. Of course, we are keeping the endpoint fixed, and this boundary term here, in this case, is just the contribution from the two points at the end of the two world lines. So for a relativistic particle, these boundary terms do not impose any problem. But I will come back to the string, either in this lecture or in the next, and then we will see that for strings, this story is much more interesting. Good, let's go back to the main part here. Okay, where were we? Yeah, we finished here. So we discussed the non-covariant action for a free massive particle. Now, this is the so-called Lagrangian formalism. There's also the Hamiltonian formalism, where we replace velocities by momenta, more precisely by the canonical momenta, and canonical momenta are defined by taking the derivative of the Lagrangian with respect to the velocity. In general, the canonical momentum need not be identical to the kinetic momentum. But if we take the Lagrangian for the free relativistic particle, then they turn out to be the same. The transition from Lagrangian to Hamiltonian formalism is by a Legendre transform. The Hamiltonian, which is a function of momentum and of position and canonical momentum, is a Legendre transform of the Lagrangian. And if we evaluate this for the relativistic particle, then in a few steps we see that the Hamiltonian is equal to the energy. And this is something that you might be very, very used to. However, I already need to caution you at this point, the relation that the Hamiltonian is equal to the total energy of a system is not true in general. In particular, it is not true once we parameterize our particle in a relativistically covariant way. And this is what we will see in a few minutes. Good. At this point, we note that there are certain things that we might not be satisfied with in the formalism that I've just reviewed. For example, what is with massless particles? We would also like to have an action principle for massless particles. How can we do this? How can we write down an action principle where Lorentz covariance is manifest? And finally, how can we make sure that the physics that we want to describe does not depend on how we parameterize our world line? We will address these questions in reverse order, starting with the question of independence of physics or of relevant information with respect to parameterization. So let's start again. We take a general parameterized curve, which mathematically is a map where we have a parameter interval, and then for each parameter value, we have the associated point in a target space, in our case, in Minkowski spacetime. So the picture that we are having here is the curve parameter is some interval on the real line, and then we map this to a curve in Minkowski space. Let me indicate this here by drawing a coordinate system, and then every point in our coordinate interval is mapped to a particular point in Minkowski spacetime. And for now, sigma is arbitrary, and then we can take derivatives of our point here with respect to the curve parameter, and this then gives us a tangent vector to the curve. But if this is a general curve parameter, this is not the relativistic velocity, but just some tangent vector. However, what still applies is that we can look at the square norm of our tangent vector, and it's positive for space-like and negative for time-like curves, and null or zero for light-like or null curves. So this distinction can be applied for general tangent vectors. Good. Now, given a general curve parameter, we can compute the length of a curve. More precisely, we can define the length of a space-like curve by the integral d6. And this expression is well defined with my convention. The integrand of the square root here is positive. So this is a well-defined expression. And you can show that this quantity does not change if I change the curve parameter and reparameterize the curve. Valid reparameterizations are all those where the new curve parameter sigma tilde is an invertible function of the old, which means that the sigma tilde by the sigma is different from zero. And you should be able to easily verify that this quantity here is reparameterization invariance, and therefore the length of a space-like curve is a meaningful geometrical, or if you like, physical quantity. You can also do this for time-like curves. For time-like curves, I need to include a minus sign here, not because the square norm of the tangent vector is negative, but otherwise it works in the same way. But for null or light-like curves, I cannot define a length-like quantity. That's why we will need to discuss massless particles separately. Good. So important to show is also the following. One choice for the curve parameter that you can make is to parameterize a curve by its length, or it's a time-like curve by its proper time. So you can, as a particular curve parameter, really use the length itself. Always you parameterize where you are by the length that you have traveled from the start. I claim that this is equivalent to requiring that the tangent vector is a unit vector with a sign depending on whether it's negative, whether it's a time-like or a space-like curve. Good. If you haven't seen this before, I recommend checking this statement of mine by yourself. Good. Now we can write down a covariant action for a massive particle. We do the same as before. We take mass times length or proper time with the same conventional minus sign. And from the previous exercise, we then know that what we have written down here is really reparameterization invariant. It does not depend on how we parameterize our curve. So it's a meaningful expression. Now there's another thing that we want to be a manifest symmetry, and this is symmetry under Poincaré transformations of Minkowski space. So let's take the opportunity to talk a little bit about Poincaré transformations. Poincaré transformations are the most general transformation which keep distances in Minkowski space the same. And they look like in formula number 30. There's two parts. One part is that we can make translations in Minkowski space, shifting by a constant vector. And then there's a linear part where a matrix acts on our vector, position vector x. This matrix must belong to the Lorentz group, for which we use the notation O1, d minus 1. And as a matrix group, the Lorentz group is defined as in formula 32. Namely, our Lorentz transformation matrices must be invertible matrices, and they satisfy this relation here, which ensures that the Lorentz scalar product is invariant. Altogether, for those who are a little bit used to group theory, Lorentz transformations and translations combine together into the Poincaré group, which is a product between Lorentz group and translation group, but it's a so-called semi-direct product because Lorentz transformations and translations do not commute with each other, but Lorentz transformations act on translations and apply a Lorentz transformation to the translation vector. Therefore, this is a so-called semi-direct product. I will from time to time make some remarks about group theoretical concepts. I don't assume that anybody is an expert in group theory. It is just a few additional remarks for those who know a bit about group theory and are interested in this. Now, carrying on with our action, we can now again make a variation and obtain an equation of motion, which I claim takes this form. And to check that this is consistent with what we had before, we can choose as curve parameter specifically the proper time. In this case, the denominator here becomes unity, and we go to formula 35, which is what we had before. Good. So we now have had some partial success. We have, at least for massive particles, a way to write down an action which is reparametrization invariant on the world line and which is Lorentz covariant. That's nice. You can also talk a bit about interactions. Firstly, mechanical forces. If the force that you have acting on a particle is a gradient force, then there's an action principle, and the additional term that is added to the action is just the integral of the potential along the world line. You can then check that if you make a variation of the action, this generates a term which is proportional to the gradient of the potential in the equations of motion, and this is then the force acting on the particle. The second important type of interactions are if the particle is charged, electrical charge Q, and is in an electromagnetic field with some vector potential mu, which is a Lorentz vector. In this case, the term in the action is proportional to the integral of the vector potential over the world line. By making the variation, we create an additional term on the right-hand side, which is a relativistic expression for the Lorentz force and involves the field strength tensor, which is the generalized curl of the vector potential A. Finally, for those who are familiar with general relativity, here is how particle motion in a curved spacetime works, or if you like, in a more particle physics language, what happens if we couple our particle to a gravitational field. This is done by replacing the Minkowski metric by the general Riemannian metric, G mu nu of x. This is then the resulting action principle, which for simplicity I've here parameterized by the proper time. And if you now make the variation, the equation that you get has the following form, which apart from the term, second derivative term that we know from Minkowski space, has this additional term, which is quadratic in the velocities, and involves the so-called Christoffel symbols associated with the metric. So if you had a course in general relativity, you will know what these Christoffel symbols are. What I should also remark here is that this equation here also has particular geometric meaning. This is the geodesic equation. So the solution to these equations are so-called geodesics, and geodesics are the curves in a curved space or space-time which generalize straight lines. In particular, they have the property that the tangent vectors along the curve are parallel to each other, and for space-like curves, that the curve has minimal length. For proper time, it turns out that geodesics are curves of maximal proper time. If you haven't heard this before, think a little bit about it. It should make sense if you think about what this means. Okay, good. But this was a side remark. Now, let's also talk about the Hamiltonian formulation in the case where we have relativistic covariance. So we proceed by defining a canonical momentum by taking the derivative of the Lagrangian with respect to the generalized velocity. And the generalized velocity is now, if you work with the general curve parameter, it is just the tangent vector x prime, which gives us this formula But as you see, the extra term which we get automatically normalizes this to a unit vector. So the canonical momentum, as in the non-relativistic case, is equal to the kinetic momentum. So that's nice. But there's one important difference, because the components of the kinetic and hence of the canonical momentum are not independent. They satisfy this relation here, which is the mass shell relation. So that means that we have what is called a constraint, a relation between the components of the canonical momentum. This has a very curious side effect. If we now compute the Hamiltonian, again by a Legendre transform, then we find that the Hamiltonian is not equal to the total energy, but is equal to 0. In fact, if you look at it, the Hamiltonian here is up to a constant. It's proportional to the mass shell condition. So the Hamiltonian turns out in this relativistic framework not to be the energy, but to be the mass shell condition. Now that's absolutely typical for any theory that you write relativistically covariantly. All these theories belong to a important class of theories, which are called constraint theories or constraint systems, and this includes any manifestly relativistic theory, it includes general relativity, it also includes gauge theories. And that might be a bit surprising and needing some getting used to, that the Hamiltonian is not the energy, and in fact is equal to 0. And to avoid confusion, I would add the following remark. The fact that the Hamiltonian is 0 should not be seen as an identity or strong relation. It does not mean that the Hamiltonian is identically 0. What it means is that configurations are physical, which are physical, must satisfy the equation h equals to 0 as an additional condition. So the way we have to see it is as a constraint, which is imposed in addition to the equations of motion. So the way we will proceed in the future is we solve the equations of motion, but we only accept those solutions which satisfy the additional condition h equals to 0. There's still a relation between such a constrained Hamiltonian and the energy in the following sense. From quantum mechanics, you will be used to the fact that if you have an observable and you are in the Heisenberg picture, where an operator depends on time, that the infinitesimal time evolution of such an operator is computed by taking the commutator with the Hamiltonian. This type of relation still holds if you have a constrained Hamiltonian. Similarly, if you do the same in classical mechanics with Poisson brackets, where the time evolution of observables is computed by taking Poisson brackets between the Hamiltonian and the observable, this is still true, except that when we restrict to physical states or to physical configurations, on these configurations, the Hamiltonian vanishes. The theory of constraint dynamics is nowadays a very wide field. It started, I think, with Dirac, who already in the 40s used relativistic strings as an examples. But at that time, it was more important that he pointed out that gauge theories and general relativity are examples of constraint systems. So if you talk about all these theories in a Hamiltonian framework, you have extra complications. Fortunately for us, we will be able to maneuver around without getting too deeply into this theory of constraint systems. Good. So let's now ask the final question. How can we include massless particles into our formalism? So far, we have relativistic massive particles, we have reparametrization invariance with Lorentz covariance, but we can only do it for massive particles so far. So the trick to also deal with massless particles is to work with an invariant volume element on the world line, and this is defined here. So we multiply the coordinates, the differential of the curve parameter by a function E of sigma, which is asked to transform precisely in such a way that the resulting line element is reparametrization invariant. Then we can write down the action 47. All these terms here are separately reparametrization invariant, as you can check. And this contains the term for the mass, m squared, but it was also perfectly meaningful if we consider m squared equals to 0. Good. Now, this action depends on two quantities, on x and on e. So we have two equations of motion. The first is by variation of the path x. This gives us a dynamical equation of motion. Second one is a variation with respect to this new auxiliary function e. And this gives us a relation on the right-hand side of 49, which is algebraic in e. And this is a telltale that since the equation of motion for E is algebraic in E, E is not a dynamical field, but an auxiliary field. In fact, if m squared is different from 0, we can solve for E, and by substituting back, we obtain the previous action for a massive particle. This shows that our new action is equivalent to the old one if we stick to massive particles. But the advantage is that we can now also work with massless particles. And to see this, we now proceed in a different way. We do not eliminate the auxiliary field, but we do something else. We choose a convenient reparametrization, or as the jargon goes, we choose a gauge where we put this auxiliary field to a particular value. For massive particles, we can choose the gauge or parametrization where E equals 1 over the mass of the particle, and then we end up with relations 51 and 52. Our dynamical equation is now as before, the equation for a free particle, and the equation of motion for E now becomes the condition that the square norm of the tangent vector is -1, but this just tells us that we have chosen the parametrization as a curve parameter is proper time, and we have reproduced the basic setting for a massive relativistic particle. For mass squared equals to 0, we can choose a gauge where E equals to 1, and then we get this corresponding set of equation where again the first equation is a dynamical equation for a free particle, and the second equation now just tells us that the square norm of the tangent vector is equal to 0, so that the particles with m squared equals to 0 are constrained to move on like or null curves. And this is precisely the dynamics of a massless particle as we know it from special relativity. What you might want to convince yourself is that you can always make changes of the parametrization which bring you into these gauges. What I also leave to you for you to think about is what about the case m squared smaller than 0? Formally, if you think in terms of particles, this would be a tachyonic particle which moves faster than the speed of light and which for reasons of causality we would reject. However, I claim there is a meaningful mathematically or geometrical application for this case. So if you think about m squared smaller than 0, these are geometrically speaking space-like curves. So we have a variational principle for space-like curves. So what might be the application of this action that we have given with the auxiliary function E, in this case, in the context of geometry? I think I'm already done with the particle part. Let me just check whether there is anything, anybody. Oh, I see I've checked the chat. Is there a specific textbook you recommend? I'll check what I have recommended on the pages, on the magic pages. My personal favorite textbooks are the one by Green, Schwartz, and Witten, which is a bit old, but this is the one from which I learned string theory. And at that time, there was also a second book which I liked when I was a student, the one by Lust and Tyson, which now has gotten a makeover and has been updated to modern string theory with all the things from the 90s already included. And this is a book by Blumenhagen, List, and Tyson. But I'll check what recommendations I have on the magic page, and I will update it with a few other titles. Okay, but these are my own favorites. Yeah, what else? I mean, there's a book by Zwiebach, but this is more for undergraduates, and this is a course for PhD students. So it's still very good if you want to look up details, and it's also very good on aspects of deep brains, which I will not cover to such extent, but overall, Zwiebach is mostly for undergraduates, and you will want to have one of the more advanced textbooks. So I'll check and put something in. Now, we have a bit of time left, about 10 minutes, so we can also now already start talk a little bit. Oh, there's another question in the chat. Can I read this here? Okay. Okay, no, it was just a thank you. Okay, good. So, yeah, but no pressure. I hope that I'm neither running too fast nor too slow. You can also give me feedback. Essentially, we have seen in this first lecture what we wanted to see, but let's use the extra 4 minutes to already think a bit about relativistic strings. So what will now change? Well, essentially, we think intuitively before we had a particle, and now we spread out the particle into something which has one spatial extension, a string, and then the word line becomes a surface, which we call the word sheet. And now we will need the mathematical apparatus to deal with this. So here are my conventions. So the word sheet is usually called sigma, and coordinates are sigma 0 and sigma 1, and I use alpha as a letter on the word sheet, whereas mu remains the index reserved for space-time, but following conventions in the string theory literature, the coordinate in Minkowski space is now a capital X. And here again, we have the picture that we can think about the word sheet as an embedded surface, meaning that I have a parameter interval, which is a sigma 1 and a sigma 0, which is then somehow embedded into space-time. Okay, yeah, let me also explain already some more conventions. So at each point in our word sheet, we will now have two directions. So I have always two tangent vectors. And we have a standard choice. So the one where we differentiate with respect to the sigma 0 coordinate is called x dot. And the one where we differentiate with respect to sigma 1 is x prime. And I take the convention that x dot is always a time-like tangent vector, and therefore sigma 0 a time-like coordinate, and x prime is a space-like tangent vector, and therefore we can think about sigma 1 as a space-like parameter which parameterizes points on the string. So if this is one string at one time, and then I go to a different parameter value of sigma 0, then I will get another embedded line, which is a string at that time. Now, I should, of course, caution you that these labels sigma 1 are just conventional labels that we put on the string conventionally. Physically, the points along a string are indistinguishable. Therefore, you might think of sigma 0 as something like time and sigma 1 as something like points on the string. But this is a particular conventional labeling of what we might mean by time and space along a string. And we must make sure that all the real measurable quantities that we create are really reparameterization invariant and don't depend on how we have labeled our points. Okay, just to wrap up my conventional choices. So sigma 0, the word sheet time, if you like, will always run in some interval. which depends on for how long we observe the string. If we observe the string for infinite time, this might become the full real line. But for sigma-1, the coordinate running along the string, I make the conventional choice that sigma-1 always runs between 0 and pi. Note, of course, that sigma-1 is in particular not related to the length of the string. In fact, we will see that the length of a string is dynamical, so it will change when a string moves around. This is, by the way, clear from special relativity, because since the speed of light is finite, there can be nothing like a rigid body in special relativity, because a rigid body would allow you to transfer information and energy with infinite speed. And for that reason, a relativistic string is not a rigid object, but something which fluctuates, which vibrates, and therefore changes in length over time. But we will see all this in more detail once we have developed the theory to the point where we can formulate and solve the equations of motion. So my alarm just went on, which has told me that I've talked for long enough. So let me stop sharing. There's currently no urgent further question in the chat. So I hope that you have liked our first lecture together. Please get in touch if you have questions or feedback. As promised, I will check that the information that is on the webpage is up to date, in particular that I write a bit more about books. And otherwise, thank you for joining today, and I hope to see you all back again, same time next week for our second lecture. Okay, that's it. Signing off now. Greetings to all and bye-bye.